Problem number 2, free response question number 2. The figure above shows an above-ground swimming pool in the shape of a cylinder. The radius is 12 feet and the pool has a height of 4 feet, as you can see in the diagram. The pool already currently contains, that's very important, this is your initial amount of water, 1,000 cubic feet of water at time 0. During the interval from 0 to 12, again, very important, we're only focusing on 0 to 12. Water is pumped into the pool, so the into rate is P of T. The table above gives the values of P of T, so it's important that we understand that this is the P of T table, and it's telling me the rate, how fast water is being pumped into the pool per hour. At the same time, water is leaking from the pool. So water is coming from the pool at a rate. So the R of T is how much water is going out of the pool. And instead of giving us a table, they give us a function that represents how fast the water is leaving the pool in gallons per hour. They also remind us of the volume of a cylinder. And so that's probably going to come into play at some point. Letter A, use a midpoint Riemann sum with 3 subintervals. Okay, again, look at the important words. Midpoint, 3, equal length to approximate, see, this is what should be going on in your head, the total. Total tells me I'm going to integrate something, amount of water that was pumped into the pool. So they're telling me not to consider water going out of the pool, but only water going into the pool. Show the computations that lead to your work. Okay, so if you look at my work below, you can see that I write an interval and I tell the AP people I am going to start at time 0 and I'm going to stop at time 12. I'm going to accumulate or total up water going into the pool because P of T was into rate. Remember, when you integrate a rate, you lose the rate. So if we integrate P of T, we're going to lose per hour, and we're going to end up with gallons. Now, since I'm going from 0 to 12, I take my interval of 12 units, and I divide it into 3 equal parts. So the common width of my rectangles is 12 over 3, which is 4. That is the common width of the 3 rectangles. Now, to get the height of the first rectangle, since I'm going with 3 equal subintervals, 2 would be the first midpoint. 6 would be the x value of the second. 10 would be the x value of the third midpoint. So the height of the first rectangle is 46. Height of the second rectangle is 57. Height of the third rectangle is 62. So from the table above, I do the arithmetic, and I find out that 660 cubic feet of water went into the pool during the first 12 hours. Part B. Calculate total, so that tells us to integrate again. Leaked out. So this time I'm going to use the leaking out rate, which as we already know is R of T, from 0 to 12. So this time, since I don't have a table, they didn't tell me to use a Riemann sum, and they didn't tell me to approximate, I'm going to do the literal integration from 0 again to 12 hours. This is my leaking out rate function, and when I integrate a rate, I lose the rate. I'm going to do that completely on the calculator. So if you look at my calculator, now in y number 1, I have the R of T rate. So I'm going to use my calculator to integrate that, and what I find out is that 225.594 cubic feet of water leaked out of the pool during that time period. So 660 cubic feet went in, 225, almost 226 cubic feet went out. Part C, they're telling you what to do. Use A and B to approximate the volume of water in the pool at time t equal to 12. Now this is where that initial condition comes in. And this is where students often forget there was already 1,000 cubic feet of water in the pool. So in part C, we take the water that was already in the pool, We add in the water that was pumped in, which we already did. This was from part A. Then we take out the water that was leaking, so this was from part B. So I'm literally taking my 1,000, my 660 from part A, and my 225 from part B, and I'm totaling that up, and that gives me how much water is actually in the pool at the 12th hour. Part D. So part C should be pretty easy if you had A and B. Part D. Now be careful. Look at your key words. Find the rate. So we're looking for a rate. So this is not going to involve integration necessarily. Find the rate which the volume of the water in the pool is increasing at time t equal to 8 hours. So we're focusing at one specific instant of time. How fast is the water level in the pool rising at t equal to 8 hours? Indicate your units of measure. Okay, so there are two things. We want to know something about the rate of the level, and we want to know something about the rate of the volume. Now they told us earlier that volume is equal to pi r square h, and the level would be the height of the water. So there are two things going on here. The rate of the volume, and if you look right here, the rate of the volume would be the in rate minus the out rate. So in other words, I'm going to take the information that they've already given me to find the rate of the volume total, and I'm going to look at P of 8, because the volume rate at 8 would be P of 8, the in rate, minus R of 8, the out rate. And so from the table above, I see that P of 8 is equal to 60. And I lost my problem. So P of 8 is 60. And then R of 8, I just got off of my calculator and subtracted and got 43.242 cubic feet per hour. It is a rate. Now that takes care of the volume rate, and then I need to find the rate that the water is rising. So that is going to be the height. So that's our related rate problem. We're going to take V equal to pi r square h. Now the thing you got to be careful with here is to eliminate one of those variables. R is a constant radius of 12. And it never changes, so remember, you can substitute that number in from the get-go. So when I clean that up, I get a real simple equation of volume is 144 pi h. So if I want to find the rate at which the level is rising, I take the derivative with respect to time, dv dt. On the right-hand side, by the power rule, I get 144 pi dh dt, which is what I'm looking for. I know from my work above that dv dt is 43.242, and so now I'm just going to use simple algebra with my calculator to find dh dt, and that is the rate at which the water level is rising.